good morning. We are going to start our last lecture for Chapter 8, and it is parametric equations. And this is one of the most important lectures in Chapter 8 because parametric equations is going to be on the CWU finals. So that's important. And then parametric equations are super cool too. So what we can do with parametric equations is model two dimensions. So we can model, so far, we've only modeled in one direction. Like we've modeled height versus time, with a rock thrown up straight in the air. We can model that with a polynomial equation, right? But now, now this is super cool. Now we can model both the x direction and the y direction of like a rock or a rocket. So this is important. Let's write that down. Allows us to model both directions, model motion in two directions. So x of t. So x changes with respect to time, and then so does y. Totally independent of one another. So x and y are separate functions. Separate functions with respect to time. Okay, so that's like super duper cool, right? So now we can do projectile motion. What do I mean by projectile? Projectile motion. So like Mrs. Owen throws a rock, right? Rock. Or rocket, not just straight up and down, but now a rocket can go both in the x direction and the y direction. So rocks, rockets, and of course cannons or something, right? Cannons, something like that. Okay. All right. So now if you're thinking this x, y, right? And you're going to have some sort of vector, right? Like that. And it's going to go up, typically, and back down, right? If you were to throw a rock, it's going to go reach a high point and then come back down and hit the x-axis again, okay? So we can do a couple of things. We can model distance, and then we can also model velocity. So let's start with distance. So distance, if you remember from your science class, or, let's see. Oh, were you able to see that before I moved it? I don't even know. Okay, hopefully you were. So distance is equal to velocity, how fast it's going, right, times time. Okay, so we're talking about velocity and time. Okay, so first let's go back and talk about the velocity vector. So here we've got a velocity vector. There's our v, and it's going both partially up and partially over, right? So it's going both in the x direction and the y direction. So if you envision like skipping stones out on the lake, right, that you're throwing it both up and you're throwing it over. Okay, so velocity vector. Okay, so for the horizontal, right, so our horizontal vector, sorry about that, is going to be v sub x, right? So now the horizontal, and I'm going to draw that. Let's draw that and see if our purple pen works pretty good here. The purple pen does not work very good. Let's try the pink pen. Okay, there, pink pen. So this piece is the horizontal, right? The x direction. And then this piece is going in the vertical. So this is our v sub y. And if we know this angle, right, we can split this vector into its two components, its horizontal component and its vertical component. You guys remember how to do that. So v sub x is equal to the magnitude of v, which we show with those line symbols, the magnitude of v times, you got it, cosine of theta, and the vertical component is the v sub y, and that's going to be also the magnitude of v, but sine. So we're using our trig functions again, right? Okay, let's put a box around that. That's important. Velocity vectors can be split up, right, into their components. And so this leads us right in to the vectors for distance. Okay, so distance is equal to velocity times time, right? So our x component, or our x distance vector, so the horizontal is going to be x. So that's going to be the velocity, which is here, right? V sub x, which is the magnitude of v cosine of theta, and then we're going to multiply it by time, times t. All right, and same goes for the y, except y has a lot more going on, okay? So y has that same component. How far, you know, did it go based on our velocity and that initial velocity and time, right? So velocity, magnitude of velocity, sine of theta times t. Now, the thing about the y component, though, is it's got something working on it, right? So you throw something, it's not just dependent on how hard you throw it. You've always got this force pulling it back to Earth. That's right, you said it, it's gravity, right? So our force pulling it back to Earth is going to be equal to 1/2 that force of gravity, we're going to call that G, times t squared. And then sometimes you'll see added, tacked on to this equation is your initial height. So we're going to call that h sub 0. Okay, and these are important formulas. So you'll want to put a box around that. Okay, and just remember that this is gravity and this is initial height. And you know, whoa, that didn't really fit, did it? I'm kind of squeezing that in there, sorry about that. Okay, so one thing, initial means what? Initial. So if they say, okay, we were initially at 10 feet, that means at the start, right? So that means at t equals 0. Okay, and so a lot of times they'll show initial velocity. They'll show that as v sub 0, okay, to show that, okay, that's at the starting point, what velocity are we starting with? And then initial height as well, which I just used, is h sub 0. So that's a good thing to kind of just keep in mind, bubble that. Anything sub 0 typically means initially, Okay, let's do a couple of examples. We'll walk you through and then you'll be ready for the worksheet. Okay, so example 1, a cannon fired at 500 miles per hour at an 35-degree angle. Find initial horizontal and vertical velocity. So we're going to use, those are our distances, right? So we just want to use these, our velocity vectors. Oops, I'm pointing at something you can't see. So velocity vectors. So we're going to go ahead, and this is just like your number 1 on your worksheet. So let's go ahead and do it. So I'm going to put a little number 1 so you guys can remember. Okay, so horizontally, we've got v of x is equal to, okay, we've got 500 miles per hour. That's the value of our vector, 500 cosine of 35. That's all there is to it. Easy peasy, right? You plug that into your calculator and you get 409.58 miles per hour. Okay, and v sub y is same thing, but we're going to use, I know you said it, sine of 35. Now, why didn't I use gravity and initial height? Well, they didn't tell us any initial height, so we're going to assume it's 0. And gravity doesn't start to work until we start going, until we have a value for t. So initially t is 0, so that term goes away. Okay, oops, you guys couldn't see it. So t would be 0, that term would go away. Okay. All right, so we're just solving for this velocity here. And so our initial velocity, we plug that into our calculator, we get 286.788 miles per hour. Oh, and I was confused. This is a distance equation, right, guys? So yeah, so velocity or time's going to be 0, so our distance is 0 anyway. So don't worry about me. I'm a little bit confused. Okay, let's do another example.